Okay, guys, welcome back again. At this stage, the thing that we just plan to do is this to execute the model that we just created on the previous tutorial, and let's see if we can just get to a convergence. As I said, we do not need to just change the data that we had. The only thing is that we have essentially the same thing. We have, I should say, the data stand model B that we had. We didn't have any even minor changes for our data block. The only thing is that we just run our model because the previous two models was called A and B. I'm just going to call this model C. I'm just going to call the stand function, and I'm just going to just go ahead inside the quotation mark, just put the name of the model which I had. It was called model C AD dot stand. And I also have to just define the data. The data is essentially there, data stand model B. Also, I'm just going to call the number of the iterations for our model. The thing is that we expect that the iterations, I should say the convergence, not to be very easily obtained. We need a higher number of the iterations because at this stage we have both the variables and both the, I should say, slope and intercepts are changing. Then as a result, I'm just going to increase the level of, I should say, iterations. I'm just going to put that to 8,000, which normally we are just going to get 4,000s for the warm-up. And also, I'm just going to go ahead to just put the number of the chains equal to 4. And by doing this, I'm just going to go ahead and execute this to just keep the model running. Then you see that the model is being started to be executed. You see that we are just at the phase of the warm-up. It may take some time, longer as we expected, as we have done that in the previous two models. Then as a result, I'm just going to stop the recording at this stage, and when the processing is done and we are ready to test our convergence after 8,000 number of the iterations within 4 chains, I'm just going to come back and just keep the lectures move on then. Okay, see you when the processing is done then. I'm just going to pause the recording, come back when this is done. Okay, it seems that we are close towards, I should say, completing the process of our stand file. It takes me a couple of more seconds, and now this is done. And now the thing that we can just do here right now, as the thing which we have been always doing, check for the convergence of our model. I'm just going to use a trace plot. You can also use the shiny stand, but I'm just going to use a trace plot at this moment for the model C. Let's see if we have the convergence, and also we are just going to use let me choose the parse. For the parse, I'm just going to use that for the U. And let's execute the file and see that what do we get. And now we have, I should say, the trace plot. You will see that the trace plot, I'm just going to zoom the trace plot that we have to check temporarily for the convergence of our algorithm. You see that here we have U11, U12, U13, and U21, and U22, and U23. Then you see that these are all values that we expected to just get from our model. You remember that the U was supposed to just be U11 represents, I should say, the varying intercepts and the varying slope for the case which is going to be, I should say, converted. And also, you see that U21 represents the varying slope of the case which is converted, which it seems far off being, I should say, converged. And also, you see U12, which, as you will see, represents the varying, I should say, intercept of the demented case, and U22 represents the varying slope of the demented case, the persons that they have been diagnosed with the Alzheimer. And also U1 tree and U2 tree, they all also represent essentially the varying intercepts and the varying slope for the case which they are non-demented. The model seems far off being converged. And also, if we just print the model, I'm just going to call that, let's say, model C. And even if I print the model, by checking the R hat statistics, we would see definitely that the model has not just been converged, and the R hat statistics for the primary use that we just have our parameters of our interest, it's essentially they should be probably more than one. You see that here we have the R hat statistics for these 6 U's. You see that the R hat, they are just going to be the last column here. We have 1.05, 1.01, 1.15, and 1.01, and 1.31, and 1. One of them, which is U22, has fully converged. But for the rest of it, we have some problems. Then essentially, the thing that happened here is now that we see that after 8,000 iterations, we couldn't just get to the full convergence. Then as a result, we have two options. Either increase the number of the iterations or also just reduce the step size in our sampling. And now the thing which we are just going to do, I'm just going to increase the level, let's say to 15,000. It depends on your power of your processor that you have on your laptop or your desktop. It takes quite a bit of a time, but we are curious to see that after 15,000 iterations, we get the full convergence. Then after from there, we can just move on to just draw from the posterior distribution and get the value, best estimates for the parameters of our interest. I'm just going to execute the line by pressing Control Enter, and it's going to be just run about 15,000 iterations. It just already started from the 0% of the warm-up in chain number 1. I'm going to pause the recording. When the processing is fully done, I get back to check for the convergence. Hopefully we get the convergence. Otherwise, we also tune the parameters to see what can we get. Okay, see you when the parameters, when the iterations call all has been done. Okay, guys, welcome back again. We are done with the processing of the stand file, which we just started back. But the problem was that I noticed that even with the previous, I should say, number of the iterations, we didn't still got the convergence. Then I just increased the number of the iterations to 20,000 iterations in the 4 chains. And also, I reduced the step size that we had to this number that you can see there. I rerun, I should say, the file. It took, I should say, a couple of hours, and it took such a long time to process it. But at the end, if I just want to quickly check for the model convergence by just having the trace plot, or you can also use the shiny stand, and you will see that when we have, I should say, the plots at this time for 3 levels of, I should say, of the converted. And also you see that U11 refers for the random intercepts for the converted case. U21 refers for the random, I should say, slope of the converted case. And also U12 refers for the random intercepts of the demented case. And U22 refers to the random, I should say, slope of the demented case. And also the same thing U13, which refers to the random slope of the non-demented case, and also U2 and 3 refers to the random slope of the non-demented case. Apparently, after 20,000 number of iterations with a very small step size, it seems that we have a very good convergence for the random slope of the converted case. We are not going to look into, I should say, to the random intercepts, but also for the better, I should say, understanding, also we can just print the model itself. And as you will see, we are just going to take a look into, I should say, the rat statistics. You will see that for the rat statistics for these 3 U's and also these ones, let me start from the U only. you see that for all the u's that we have, we are just for some of them, we are so close to the optimal value that we were looking for, but for some of the other ones, it seems that we do not have the optimal level of the convergence. We could also still continue by increasing the level of the iterations. Let's say we can add, let's say, to 25,000 number of iterations, and also by 1 decimal, reduce the number of, I should say, the level of the step size to see that what's going to happen if we just get the convergence for sure, because as we just increase the number of the iterations, and you can compare that from the previous one, we see that the convergence at this 20,000 number of the iterations now seems even much better. We can have a better, I should say, results if we increase the number of iterations to 30,000, depending on the computational power of your PC or your laptop. Now, let me just move on and do the things that we had planned here to check, I should say, for the level of, I should say, slope. If we get something beyond the expectations that we have, we can just go back to increase the number of the iterations. I recommend you also, if you have some time, increase the number of the iterations to 30,000 and reduce, I should say, the step size to 1 decimal. At this stage, I just want to check to see the results, because we are so close to the convergence to see that maybe we get the results as we expect. In order to do that, I'm just going to do the code which we had before. For the previous case, for the random intercepts, copy paste it here, and in order to save the time, to make some minor changes that we have. Okay. Now, previously we had, I should say, these ones. I'm just going to take it down, but starts with, I should say, with the posterior that we can just extract. Posterior, I'm just going to call that posterior model C, which is going to be essentially the extract from, I should say, the model, the extract of the model that we just had it here, model C. And let's execute the line to see what do we get by pressing Control and Enter. And when we do that, we see that the posterior for model C, it's a huge file of, I should say, of 7 elements. Our parameter of our interest for us here is essentially the U, which, as you see, that's a matrix of 40,000 rows of 2 by 3. Remember, in order to just get the extract, I'm just gonna look into that case one by one. I'm just gonna come here and see that what do we mean by each one. If I just go ahead with the posterior of the model C, and I'm just gonna extract only the U, but for us, U here has, I should say, 3 components there. The first element here refers to the number of the rows, which we are just gonna stick to the one which we had there. We had, I should say, 40,000, we're just going to keep the 40,000. And I'm here just going to go ahead, and as you can see, we have for the second elements, we have 2, which one refers for the random intercepts, 2 refers for the random slope. I'm just going to go ahead with the number 2, because our parameter of our interest is going to be to see what is the rate of the brain atrophy, I should say, at 3 different levels of, I should say, the patients in our group. If I just put number 1 here, the thing that we're just going to get, it's 1 refers for the converted case that initially we had decided on. If I execute the line, we are going to see a huge number, a huge array is going to be created. We are just going to go ahead and check that, I should say, to take the mean by using the Monte Carlo estimation and execute the line. And the thing that we're going to see a number which, although it doesn't, I should say, it's a minus sign, which it means that this is going to be a decrease. That's exactly what we wanted. And we can call that here, we can just call that converted rate, which it shows that the slope that we are expecting. Let me erase these ones here first. I can just paste them back again. And this one, the number which we got here, which is going to be minus 1.36, it essentially refers to the number which is going to be the rate of the decrease. It means that by any number of the years that the person is going to getting old, the brain is going to just, I should say, experience the atrophy by that rate. Which it's going to be, I should say, a little bit up, because I think the reason is that we didn't meet the full convergence. The rate is going to be something less than 1. Otherwise, it doesn't make sense at all. And also, we are just going to go, but also the conversion, it's not our parameter of interest. What we're looking for is going to be for the groups between demented and non-demented. I'm just going to do the same thing here again. I'm just going to go with the posterior model C. I'm just going to just extract the U, and I know that the U, I'm just going to take all the rows, which is going to be 40,000. I'm just going to get to number 2 here because it refers to the random slope. I'm just going to get number 2 here, which by our convention refers to the demented cases. I'm going to take, I should say, the mean of all these 40 throws and all these 40 estimates that we had. And I'm just going to call that the demented rate of the atrophy. I'm just going to execute the line, and let's see that how much do we get. That's a very reasonable thing. The rate is going to be minus 0.0025. That's the thing which we expected, because it shows that the brain, by any number of the years, after 6 years of old, any year that the person ages, if he is demented, his brain volume is going to be decreased by that rate. Also, we are just going to move on and check the same thing again for the non-demented cases. We check the posterior. For model C, I'm just going to extract the U, and I also take all the 40 throws. I'm just going to stick with number 2, which it refers, I should say, for I should say the random slope, and I choose number 3, which, as we know, it's going to refer to, I should say, the non-demented case. I'm going to take the mean of all those 40 estimates and store all the thing into an object which is called non-demented rate. I'm just going to execute the line, and let's see how much do we have for the non-demented rate. You see that it's going to be a little bit, I should say, far off, because for the non-demented rate, you see that it's going to be 2 U of 2 and 3. We didn't meet the convergence, and that's the reason that I should say we have, it seems that the brain is gonna increase as the person's after 6 years of old, they're just gonna age by 1 year. That's not a realistic number, and the reason for that is that because the model that we had is not fully converged. Then as a result, I'm just gonna also, before we just move on to the next tutorials, I also recommend you do the same thing. I'm just gonna just increase the number of the iterations to see that when we just get to the convergence for also for U21 and U22 and U23, then when we have the convergence back, I'm just gonna continue with the tutorials and show that essentially the rate of the brain atrophy, it's gonna get more realistic than the one which we have. But essentially by this tutorial, we followed the same systematic, I should say, procedure in order to see that what do we mean by the random slope when we just look into the variation within the group levels then. Okay, I'm just going to increase the number of the iterations, and we get the full convergence. I get back to you to share the results with you. Okay, guys, welcome back again. I just reiterated, I should say, I increased the number of the iterations to 30,000, and I just got the number of the chains to 3 because I just wanted to be very efficient in terms of, I should say, the time, which that's going to take for, I should say, for the convergence. And I increase, I should say, the step size to 1 more decimals also. And you see that the convergence that I just got, when I just got the trace plot, you see that when I just get the trace plot, it takes a couple of seconds. That's right. You see when I just get the trace plot. And also when I zoom that, you will see that just it shows a higher, I should say, level of the convergence. And also we can just show that also by just having, I should say, the R hat statistics in order to show that the convergence has happened. I'm just going to go all the way up there, and you see that the R hat statistics from, I should say, for specifically for the parameters of our interest that we have for U2, which is going to be the random slopes, it's all shows, I should say, adequate level of the convergence. Then I should say at this stage, we assume that the number of the iterations of 30,000 with that level of, I should say, control for the subsize, it achieves us the convergence of our model. Then as a result, when you just extract, I should say, the posterior distribution, and from there, you just come, I should say, the converted rates of the brain atrophy, you will see that for the converted rate, the number that we get is going to be minus 0.04, which is going to be something which we expected to have, which it means that for the conversion level, the brain atrophy is going to be for each year that the person ages, it's going to be the reduction, I should say, of the brain volume of 0.047 unit then. And also, for the brain atrophy and the rate of the atrophy of the persons who are demented, you are going to see that it's going to be 0.0025, which it also shows that, for example, a reduction of the brain size, and also the same thing for the persons who are non-demented. You see that also again, it's going to be, I should say, we have the brain atrophy of that level, which is also a minus number, which is the adequate number that we were looking for, because we noticed that from the previous, I should say, talk that we had, that we were expecting to have, I should say, the random slopes to be a negative number, which shows that by the increase of the age, we should have a reduction of the whole brain volume, and also it should be less than 1, because it should be between 0 and 1, because it's going to be a reduction of the volume then. Essentially, after this long journey that we had for achieving the convergence of our model, we were able to show that the random slope, which refers to the rate of the decrease and the brain atrophy between, I should say, different levels of the group, that they are going to be demented, non-demented, or converted, we achieved, I should say, an adequate rate of their brain atrophy then. At the next tutorials, we are just going to add one more level of hierarchy and see what are going to be the results that we're just going to get there. I can't wait to see you at the next tutorial, and thanks for staying so long for this tutorial.